This work is part of the bilateral Peruvian-German research project SASCA that is financed by the Federal Ministry of Education and Research in Germany. Bivalve mollusks, such as mussels, clams, and scallops, represent valuable marine resources that have been harvested for a long time. Aquaculture recently became an important alternative to avoid overexploitation of natural populations. By now, bivalve aquaculture production takes place in many coastal ecosystems worldwide, providing livelihood to thousands of people. However, the development has often been a bottom-up process, without systematic planning or management involved. Nevertheless, overstocking of culture combined with critical environmental changes may result in bivalve mass mortalities, and this can ultimately cause severe consequences for the entire ecosystem. This is why knowledge on ecological thresholds to production for an ecosystem under the impact of such cultures is crucial for long-term sustainability. An important concept in this context is the ecological carrying capacity that is defined as the maximum amount of cultured bivalves that does not yet cause any negative impacts on the ecosystem. As yet, most approaches for the definition of such a threshold have focused on bivalve-phytoplankton interaction, neither considering the interaction with other species in the system nor the overall impact on the ecosystem itself. We present here a truly ecosystem-based approach for the estimation of ecological carrying capacity to bivalve culture and aim at contributing to the ongoing discussion of the important topic of sustainable aquaculture. Our study system is a large bay in northern Peru which has recently developed into a hotspot for scallop culture. Here, the bivalves are cultivated in bottom culture, involving about 5,000 artisanal fishers and around 20,000 additional personnel that is working in the entire production chain. The activity therefore represents an important socioeconomic factor for the region. However, intensity and area extent of cultivation activities continue to increase. Accordingly, the ecosystem-based assessment of the current situation and the determination of long-term sustainable limits to culture for the bay are crucial. Our approach involves the construction of a trophic food web model that comprises of the different functional groups found in the system. In this model, both benthic and pelagic species are represented, and the species groups are interlinked via trophic connections. The construction of the trophic web was done via a mass-balanced approach as provided by EcoPath. The further expansion of culture activities was explored by forcing scallop biomass to increase to 4 different levels. The impact on other functional groups and the ecosystem was investigated by the means of ecological network indicators as calculated by EcoPath and by looking at the development of functional group biomasses. The results suggest that phytoplankton availability does not represent a critical factor for culture expansion in this system, which is in contrast to other studies. More importantly, culture expansion may cause scallop predator biomasses to increase. And this represents in turn a top-down control on other groups of the system, such as competitors of cultured scallops, and those groups decreased in biomass. The ecological carrying capacity was defined as the maximum amount of scallop biomass that would not yet cause any other group's biomass to fall below 10% of its original standing stock. This concept is based on the definition of a depleted stock in fisheries science. A scenario was considered valid if all groups stayed above this threshold. According to our explorations, the current magnitude of scallop bottom culture for this bay does not yet exceed ecological carrying capacity. A culture expansion would, nevertheless, induce changes in the entire trophic web. Exceeding scallop biomass levels of 458 tons per square kilometers may cause other functional group biomasses to fall below the 10% threshold. The loss in biodiversity that this would represent may then change ecosystem functioning and cause the system to be more vulnerable towards future disturbance, which is a state that would not be desirable from an ecological point of view and should be avoided. Results of these studies are expected to guide both local fishers and managers in their challenging task of finding sustainable long-term levels for this important socioeconomic activity in Sechura Bay. The ecosystem-based estimate of ecological carrying capacity was here defined as the maximum degree of tolerable change in the food web surrounding the culture. The approach presented here is expected to be applicable to other marine ecosystems exposed to bivalve culture, in order to ensure the long-term sustainable use of these valuable marine resources. Thank you very much for your attention. If you have any question or would like to discuss our work with me, please come and find me. I'm around for the conference, or write me an email.